Okay, so good evening, everyone, again. Welcome to the week 12 of Introduction to Basics of Semiconductor Microwave Devices. And probably this is, we are moving into the final week of, that is week 12 of this course. And it has been a long journey since week one. So, what we are going to do is that we are today going to cover the basics of passives in microwave circuits, a little bit about small signal models, inductors, capacitors, and something called as de-embedding. And we're mostly going to talk about the passives. So I'm Shazan Bhatt, and I'm a direct PhD student. And what we're going to see today is that we are going to cover all of the topics which have been which I have basically marked here in the bold letters. So that is what we will be covering, and most often, I should say, there will be one more extra session this Wednesday. I should say next week, between 11 to just check between 11 to 1 p.m. So that anybody who is having some doubt or anything, we can even recapitulate the entire previous session so that we can actually finish this course. And if anybody has any doubts, or I'll be briefly talking about what are the open research areas, what are the open research problems in this field, and how you can basically enter into the research field in the microwave devices. And this is particularly we're talking about devices, not the circuits aspect, because we mostly cover the device aspects of this course. So uh, that's what I'll be talking in the I should say in the next week. But this week, this session, this will be about the last session and solving the problems of this particular week. They are quite straightforward problems. If you have gone through the lectures, you might have also seen. I should say a couple of numericals. The rest of them are theoretical questions, just straightforward from the sessions. But I'll be trying to briefly discuss about what professor has tried to cover in this particular session. Let me just there is some issue. Okay, let me just turn off this and share my screen. Okay, all right, I hope it's visible. Okay, so what we are going to cover today are passive devices. So where are those passive devices used? They are used in filters, they are used in power amplifiers, they are used in MMICs, whole lot of stuff. So these passive devices can be used to, let's say, create some delays, let's say, increase, I should say, change the phase of the incoming waves. They can also be used to mix certain forms of the waveforms. We're talking about the microwaves here. So the basic, let's say, for example, if you have an inductor and you have a capacitor and it's connected to some load, let's say, for example, then you know from your basics that the inductive reactance, which is the impedance, is something denoted as omega times the inductance, and the capacitive reactance is given by 1 over omega c. That means if you have at high frequencies, that means omega tending to infinity, the xc tends to 0. That means at high frequency, the capacitor behaves like an open circuit. I should say, the impedance tends to 0. That means it behaves like a short, not an open. That means it allows everything to pass through it. So that's the behavior of capacitor at high frequencies. Similarly, for an inductor, if omega tends to infinity, you have XL tends to infinity. That means there is a huge impedance offered by the inductor. That means the inductor will behave like an open circuit at that particular frequency. If the omega tends to infinity, this will behave as a short. These are just the basics you have been always taught from the basics of principles of electrical engineering, whether it's in undergraduate course, whether it's 10 plus 2 level. You have always been taught about the current flowing through the capacitor, the displacement current, and all of those things, the magnetic energy stored in the inductor, the electrostatic energy stored in the capacitor. So all of these things, they are that I'm not going to cover. That is just the basic thing, what you should be knowing at least. So if we have, let's say, for example, let's talk about a metal. If we have a metallic bar, let's say this is a metallic bar where this is, let's say, this is the thickness of this metallic bar, this is the W width of this metallic bar, and this is the length of this metallic bar. So this has three dimensions. Okay, then you know from the basic electrostatic physics, the resistance is rho L over W into T. Okay, so this is actually rho L over A. So this is basically the resistance is dependent on the dimensions of it. Okay, at least we are talking about the macroscopically. We don't talk about something called as mesoscopic, or we don't talk about what happens at microscopic level, or we don't talk about nanoscopic things. We are not talking about these things, okay? Because it might seem that even Ohm's law is not valid at nanoscale devices. So we are not talking about that, okay? We're talking about the macroscopic device where the Ohm's law holds, where everything classical holds. We're not talking about any quantum effect. So this is the resistance you have been talked about. So that's why uh, what we normally use if we have to include the resistance, why do we want to include the resistance in, let's say, for example, any MMIC you make or any microwave circuit you make? Then you want to include the resistance by I should say choice. Sometimes resistance is not I should say it's not something you would desire, but sometimes you desire it. Why? Because you want to modify the time constant, which is R times C. So if you can modify the resistance, you can include it, you can change the resistance, you can modify the time constants and other things. You can modify the delays. Okay. For example, most of the time people use something called as tantalum nitride based resistor, titanium nitride, or Ti gold based these metallic contacts in order to change the resistance. Okay, so you can tune those particular values. Now, for example, what you have is you have, for example, if you have a current flowing through a conductor, let me draw another conductor. Let's say, for example, you have a conductor like this, which is almost like a cylindrical wire. So if you have a very high frequency wave passing through this conductor, we're talking about electromagnetic wave, which is having the electric field component and the magnetic field component, and this is the direction of the propagation. Okay, so this is like a TEM wave, transverse electromagnetic waves. Okay, what happens basically is that because electric field gives rise to the potential, the magnetic field gives rise to the voltage. So these are like reinforcing each other, electric and magnetic fields. So when the electromagnetic wave propagates through this wire, it creates something called as back EMF. Okay, that you have that this also you have talked about in the previous classes. So back EMF it generates the current which opposes the original currents. Okay, which opposes the flow of current. Okay, now what happens is that as a result of which there is a gradient, or I should say, the current starts to flow more towards the periphery of this wire rather than towards the center of this wire, so that you have more of the current flowing through this periphery rather than near the center. So that this will be the distribution of the current flow. So the flow of the current is through the periphery of the device and it starts to flow in this device. That means if you have a, let's say, a metallic bar of certain thickness, then if you feed it with, let's say, electromagnetic wave, we're talking about microwaves here, okay, then the current is going to flow over the surface and it's going to penetrate over into the bulk or into the depth very minutely, and depending upon what frequency, depending upon the resistivity of this metal, and the depth is called as skin depth. Okay, up to which it penetrates into the wire deeper from the surface, from the periphery. That is called as skin depth. Okay, or it may be also called as penetration depth. It's also called as penetration depth. It's almost like similar to that of how light behaves in a medium. Okay, or rather, I should say when you have a light and light interacts with the metal. Let's say you have a metal. Let me draw it like this. Let's say this is metal. This is the thickness of metal. Let's say this is z direction. If an electromagnetic wave comes in, let's say for example this is light, some light wave. Okay, if it hits the metal, metal is highly reflective. Okay, it does not transmit. At least if the thickness is quite quite large, larger than that of the penetration depth of the wave, then you know the electromagnetic wave penetrates up to certain depth towards the into the metal. And this is basically called as penetration depth of the electromagnetic wave of EM wave. Okay, and it is basically, if for example light is coming and it is attenuating inside the medium, this is basically governed by the absorption coefficient of the medium. Absorption coefficient of the medium, which is denoted by mu. And you can write mu as 1 over, let's say, delta, where this delta is something called as penetration depth. So this mu has units of 1 over meter because this penetration depth is in meters. It has a units of length. So penetration depth tells us up to how much depth the wave penetrates into the medium. This is almost like a similar thing here. This skin depth basically tells us up to how much depth from the periphery or the surface does the electromagnetic wave penetrate. For example, if you have a, let's say, for example, this is the bar of a rectangular bar of metal, and if you draw, if the electromagnetic wave is penetrating, if the electromagnetic wave is traveling over the surface, then if you, let's say, draw the profile, if let's say, for example, we draw a profile like this is z direction, this is the amplitude of electromagnetic wave, then it will exponentially drop inside the medium. Okay, and this will denote the skin depth up to which the amplitude basically falls over to 1 by e value of the maximum. That is what we are going to prove. It's basically simple from the exponential dependence. That is the concept of the skin depth. Okay, but here it is because of it's because of the back EMF which opposes the flow of the current and makes the distribution such that the most of the current flows towards the periphery. Now you have, for example, the here in this case the skin depth is basically approximately given by under root of rho over pi frequency times the permeability of the medium. So you see that skin depth depends upon the resistivity. So higher the resistivity of the material, this is the material constant. This is the material dependent parameter. Okay, it's not resistance, it's resistivity. Okay, and and its units are ohm meter. So the pi is a constant. It depends upon the frequency. So if you have higher frequencies, the penetration depth or skin depth is smaller. Okay, that means if you go larger or larger in frequency, smaller will be the penetration depth. For example, if you talk about this case, for example, if you have this, let's say, for example, is frequency f1, then this is, for example, let's say this is frequency f2, and then this is frequency f3. Okay, then that means F3 is greater than F2 is greater than F1. The more the frequency, smaller will be the depth of penetration depth. That's why you see most of the time the metals are highly reflective in the, let's say, ultraviolet regime. If you go for the ultraviolet wavelengths, which are 325 nanometers, they are huge, almost of the order of 1000 terahertz frequencies. Compared to that of if you see for the infrared rays, which are around 800 nanometer wavelength, this is around maybe few terahertz. Okay, then there is somewhat penetration of that particular wave into the medium. Okay, now here in the optical domain, we define these things in terms of the refractive index, which is basically the real part of the refractive index plus the imaginary part of the refractive index. So that is a different thing. Here, this is this in terms of the optical things, this is basically called as attenuation coefficient. But it plays a similar role. What happens basically in case of these microwave devices? What the role played by this particular skin depth? That is the similar role played by these in the optical domain, because in that case we are talking about very huge frequencies. Okay, now this is the particular important thing what you need to understand, because there's a question based on this particular equation or the formula, which is basically the frequency dependent as well as the permeability dependent. In this, the resistivity and the permeability are the material constants, are dependent upon the medium. Okay, now the question is, why do you, if this is the case, for example, if you have a, let's say, a gold, and you are feeding it with some microwave, and the microwave is going to travel over the periphery of the gold, and let's say, for example, the skin depth is maybe 200 nanometers. I'm just assuming, let's say, assuming. Then let's say this thickness is here maybe 2 microns. And why do you need 2 microns? Why 2 microns? Because the rest of the, let's say, up to this 1800 nanometers is going to get wasted, because no current is going to get flow in the other 1800 nanometer part. Okay, on the current will be only carried by this part only. Okay, depend based on this concept. The why is basically this thickness required, because most of the time not only AC is flowing through these metallic wires, you also have DC flowing through these wires. And DC does there is no such effect like this skin effect in case of this DC. That takes place through the bulk, and that is basically travels through the bulk of this particular metal. That's why you require a huge, at least a certain thickness in order for both AC as well as DC to travel through these metallic wires. Okay, just like if you remember, for example, you give certain bias plus certain some small signal or maybe small signal. This is AC. So this bias is DC. So these metallic lines have to carry both AC as well as DC currents as well as voltage. So that's why you need to design the metallic wires accordingly. Okay, now for example, you have previously studied about on chip transmission lines. Transmission lines that was basically discussed in the previous week. The on-chip transmission lines basically uh, all of the inductors and the capacitors are implemented by this. So you implement all inductors and capacitors using these transmission lines in case of these integrated circuits. And one of the things you studied about was microstrip, the microstrip line. Microstrip line is something like if you have a substrate and you have another layer of, let's say, a metallic layer over it with width W, and for example this height is H here, and there is relative permeability of this medium, which is relative permittivity of this medium, which is epsilon R. So you have studied about it in the previous session, and this almost behaves like a I should say, whenever the microwave flows through this region, there will be leaking of the electric field, and the electric field lines will leak into the space, as well as most of the field lines will be inside the dielectric, but there will be also leaking field, which is basically the fringing field outside the outside this particular domain. This is basically, I should say, detrimental. That is what we don't want. This is we don't want. Okay, we want most of the field to be penetrated inside the dielectric. Okay, this is just this almost like these field lines are basically these are like lossy components because they are just coupling in the free space. They don't have anything to do. Okay, most of the lines or most of the field should be penetrating in this particular medium. Now, you talked about previously, whenever, for example, we have, for example, this is air having refractive index epsilon. Let's say this is epsilon one, this is epsilon r. Then you talk about something called as effective refractive index, wherein you talk about the both of the refractive index simultaneously because of this leaking field into the air. So part of the electromagnetic wave is in the air, part of it is in ground. So you define something called as effective refractive index. Okay, it's just like you define something called as effective mass. Whenever the electron is in the lattice, okay, whenever the electron is free, you don't need any effective mass concept. You have similar, just simple the free electron mass. Okay, whenever you put the electron inside the lattice system, because of all other effects of the lattice, because of all other ions acting on it, the forces acting on it, you define something called as effective mass, so that you can take into account all of those forces. Okay, that is the similar thing you define something called as effective permittivity, and they almost play a similar role here because whatever the permittivity basically it attenuates the wave, whatever the wave is traveling through it. That is the similar role played by the ions in the lattice. The ions basically slow down the electrons, whatever the impurities, whatever any scattering takes place inside the system, that basically slows down the electron. That is the similar thing done by the permittivity or the refractive index. Refractive index basically slows down the light inside the medium. Okay, we define something called as effective permittivity, and if you see what happens basically when we draw the effective permittivity versus the dimensions of this, the dimensions are basically the ratio of W over H, which is very essential when you fabricate some of these microstrip transmission lines. Okay, so this ratio has to be taken into account, and based on this ratio, basically you can tune this effective permittivity value. So if you see, let's say for example, you have certain values of these effective permittivity, just like this, And you can draw one more axis here, which is basically the impedance axis, which is the characteristic impedance. And if you show the same variation of it, let me draw it like this. Basically, I have draw it with different colors. So the blue one is characteristic impedance. So its variation is something like this. And if you have the effective permittivity, which is shown in the red color, it varies slowly, but it varies as a function of these dimensions. And in this direction, let's say we are increasing the epsilon r step by step. Okay. So what you see from this figure is basically if W by H increases at, let's say, for example, at constant epsilon r, you have a constant index, you have a constant permittivity of the dielectric, then you see that effective dielectric permittivity basically goes on increasing. And what does that mean? That means you have more of the permittivity of this particular ground plane, or whatever you call it, ground plane or substrate or whatever you may call it. Okay. So, and how can you increase basically this ratio? Either you can increase the W, but that is not usually desired because that is going to introduce more of the resistance. If you go on increasing the W, that is going to affect the resistance as well. And if you can, let's say for example, edge reduce the edge, that means thin down the substrate, or what you call as ground, let's say ground or substrate, whatever you call it. That can be basically done in order to tune this effective permittivity value. Okay. And that means effective permittivity increases. That means more electromagnetic wave is confined into the substrate. That is what we basically want. So if epsilon effective is more, that means more of the electromagnetic wave is confined to substrate. Okay, that means the leaky component which is in the air, which is basically this component, it reduces. That's what basically what we want. And the characteristic impedance reduces, and this all happens if you go on increasing this particular ratio. So that's why in terms of the fabrication, people tend to basically iterate and see and thin down the substrate most of the time in order to see how this electric field profile can be tuned. And most of the time, this is basically initially simulated in order to get the desired values of W by H, where the field penetration into the space is very less. And you can do any of the simulations using, maybe let's say you can use console multiphysics software, you can use maybe ADS, or you can use any of the tools that solves the Maxwell equation, applying the boundary conditions at this particular place and that at this particular place. And you can basically see those field profiles in order to understand the confinement of the field, as well as its penetration into the dielectric and leaking part into the air. So that is basically done in those particular softwares, and then you go on fabricating these layer by layer, and you control the dimensions. And most of the time, it's quite a simplest fabrication process, rather than if you make a full FET. That is a little bit challenging, but these things are microstrip lines are simpler than that of the field effect transistors. And now, if you talk about, let's say, for example, you have the inductance basically comes into the picture in these particular, because whenever you have a metallic line and you have these currents flowing in these metallic lines, you always have the inductances, you have the capacitances, and resistances is always there, because these are just like the transmission lines. So you have the resistance, you have the inductance, you have the capacitance, and you need to solve those transmission line equations, which we have talked rigorously in the previous sessions, which even the professor has mentioned in the previous weeks. So we have talked about those transmission line approach. Basically, you can basically solve the KVL, KCL. You can write the loop equations in order to find the currents and the voltage. Okay, but there is a particular relation which basically relates the, let's say, for example, the inductance of this with respect to the length of this particular wire, length of this particular strip. So it is basically a relation which is something like this: logarithmic of 8h over w plus w over 4. uh, and I don't know this whether this is, I don't remember where it was this. No, this is basically w by h. Okay, so the relation basically looks something like this. So it basically says that if you increase the this particular thickness, or if you reduce the W, which is basically this thing, so you can basically tune the inductance of it. You can tune the inductance, or you can increase the inductance of this particular. particular system. Now, why is this necessary? Because, for example, it may be necessary in order to tune certain delays. It may be necessary in order to tune the phases. It may be necessary in order to couple the electromagnetic waves. Okay, these inductances values are basically storing the magnetic energy. Okay, that's what you have been basically taught from the from your basic undergrad courses or 10 plus 2 levels. Okay, so for example, if you have the inductance value which is much less than the capacitance, okay, you can basically have more radiation loss in the air. That is basically what the tuning of these particular parameters mean. If you can tune these parameters, you can basically control the radiation loss into the air and its penetration into this particular substrate. This is what you mostly want, and this is what you don't usually want. Sometimes you want the upper part, but this is completely cannot be completely neglected, or it cannot be completely omitted rather. That's why you most of the time when you are using your phone, there is always a component of the electric field that is basically near the surface of the chip. That's why most of the time you might have heard that you should not just keep your phone near your pocket or near your maybe heart or something, because these field lines are always there. They are basically field lines in the space, in the free space around that particular chip. Although it's not, I should say the let me just, it's not the what should I say? The penetration into the space is not much higher, or I should say greater, but still these field lines are there that can basically interact with the already existing field lines in your system, maybe a biological system or any other electromagnetic system. It can create electromagnetic interference as well. Maybe the some external electromagnetic wave can couple through these electric field lines, and it can maybe create certain interference in these particular microstrip lines, whatever the wave may be flowing through these microstrip lines. There are a lot of other effects, and but this is definitely a lot more studied effect in the literature. Okay, now how do you make let's say for example, if you want to make a inductor, but you don't want to make an inductor just like a single strip of a metallic wire. Why? Because you need a huge area in order to create the huge inductance. Okay, because inductance is proportional to the area, just like from your basic electrostatics. And that's why what you don't do, you don't just put a single strip of a metal. If you want to create an inductor, you don't just put a single strip of a metal and let it behave like an inductor, because the current will be flowing and there will be magnetic fields around it, and it will behave like an inductor. You don't do that because you will require a very huge area as well as the dimensions of this particular wire. What you do, you make something called as a spiral inductor. That is the most commonly used inductor in basically MMIC design. But these are mostly fabricated at a microfabrication level. So these look something like this. I'm just showing I'm not showing the thickness part. So these look something like this. These are something called as spiral inductors. Basically, it will look something like this. This is the exact schematic of it to show the thickness of it. So these are so this is basically the thickness of these metallic lines which are basically deposited that will behave like an inductor. And everything is going to matter. This spacing, the thickness of this, and this particular dimension, everything is going to matter because there will be current flowing in the system. Let's say the current is flowing here in this direction, in this direction, in this direction, here it's in opposite direction. Whenever the current is here in this flowing in the same direction, it will basically reinforce the inductance. It will increase the inductance a little bit. It's going to affect the inductance. Everything is going to matter, and these dimensions basically, which are basically these particular double-headed arrows, they are going to determine how the losses will take place, because there will be eddy currents also flowing in this system. Okay, because you now have you have made a loop of these currents, and now the eddy currents are going to oppose the original currents. That is what you have also taught in the you have also studied in 10 plus 2 levels. So all of these dimensions are there in order to control the losses, in order to control the resistances to the current flow. Okay, they are really important in order to control the losses. Now, for example, if you have, for example, these inductors are most of the time used for as a bias fields or impedance matching. For example, if you have a large area, you can increase the inductance. That's what you know. But what it does is that it limits something called as self-resonance frequency. Self-resonance frequency of an inductor. What is self-resonance frequency? It's nothing, it's the maximum limit of a frequency up to which an inductor behaves like an inductor. Okay, just like you know that impedance of an inductor is basically omega times L. So if you go on increasing the omega, the XL goes on increasing. And there's a point in the frequency beyond which inductor no longer behaves as an inductor, and its inductance becomes negative, so it behaves like almost like a capacitor. Okay, then it starts to allow the current flow. It's weird, but basically this happens. Okay, this and that particular frequency is called a self-resonance frequency. That means, for example, if the frequency is greater than the self-resonance frequency, the inductor no longer behaves as inductor. Okay, that is why you want the frequency, the working frequency, to be less or equivalent to the self-resonance frequency. Self-resonance frequency. We will see there's basically a plot of inductance basically goes to maximum, not like this. If this is, for example, this is, let's say, inductance in Henries, and this is the frequency, let's say frequency in gigahertz, then inductance basically reached a maximum, that it changed the sign and it looks something like this. So this is positive inductance, this is negative inductance. So there is a sign change around this particular frequency, which is the self-resonance frequency of an inductor. And there is one more plot basically, which is basically a quality factor of the inductor. Quality factor basically here in this particular domain, it just shows you how well an inductor behaves like an inductor. You might know about the quality factor in case of a resonance. In case of resonance, if you have at particular frequency the amplitude reaches maximum, okay, then you have the quality factor basically determines how sharp is this particular feature. Okay, that is basically the quality factor. Here the quality factor is simply, the quality factor is the desired output divided by what is basically undesired, not losses, undesired, undesired. Okay, that is the quality factor. And when you plot basically the quality factor in these particular systems, you see the quality factor basically reduces beyond certain frequency. That frequency is again called as self-resonance frequency. So the domain in which you want to make the inductor work should be this particular spot. This is basically the sweet spot of the where you want your inductor to work. So this particular frequency range will be the best suited for your inductor, so that your inductor behaves as an inductor and it should not create other parasitic effects. It should not go into the high frequency regime beyond the self-resonance frequency. Okay, so these are certain characteristics of these particular inductors which are basically used in microwave devices. So for example, if the I should say self-resonance frequency, if the self-resonance frequency, I should say, ideally should be large. That means you want this point ideally to be at a very higher frequency. You don't want the non-ideal effects to take over earlier. You want this point to be higher in frequency. So that means this particular frequency should be large. Okay, that means for example, I should say if there is large area, that means just like I told you here, if you have a large area of an inductor, it limits the self-resonance frequency. That means if you go on increasing the area, the self-resonance frequency reduces, and you have the capacitive coupling coming into picture. You have the capacitive coupling coming into picture. Okay, because you see that, why does the capacitive coupling comes into picture? Because you see that there is current flow in this direction, there is current flow in this direction, in this direction, in this direction, and this is the metal, this is the metal, there is a spacing between the metals. So you always have a capacitor, just like you have a two transmission lines, and there is always some gap, let's say some D. You always have a capacitor there. And here we are talking about at a nano fabrication level. Okay, these capacitors are always their capacitive couplings, but they don't come into picture unless and until you go to a very high frequency. So that what happens at that very high frequency, the inductance becomes very smaller, and the capacitive coupling comes into the picture and becomes dominant. Okay, so then it's dominant by the capacitive coupling, so that this becomes negative, and you have a huge capacitance coming into the picture. Okay, and ideally, when you talk about these inductors in case of MMICs, it's not just like a simple inductor what we draw. It has a, I should say, something called as model of an inductor, just like a equivalent circuit, I should say. Just like you have a, let's say, for example, if you have a diode, you have an equivalent circuit of a diode, something like this. Okay, you know about it. Okay, then maybe you talk about, for example, this is not like this. What am I showing? If you have a diode, then you can draw it, let's say, for example, in if it's an off condition, you can draw it like a switch with a certain resistance. Okay, you close the switch, the current is going to flow. This is like a PN junction diode. You apply the positive, you apply negative here, the current is going to flow. You apply negative here, positive here, current is not going to flow. Okay, similarly, you have the equivalent circuit of a, let's say, a BJT. BJT. Let me draw it like this. You have an equivalent circuit of a BJT using maybe the hybrid model you have studied, the hybrid pi model you have studied. Those are basically the equivalent small signal models of the transistors. Similarly, you have the equivalent model of FETs, which are the field effect transistors. Similarly, you have the equivalent model of this inductor. How do you model it? You model it, let's say, of resistance, an inductor, and then you have a capacitor, which is the substrate capacitance. This is the metallic resistance, which is because of the metal. And this is the original inductance. These are all other components apart from the inductance are parasitics, what are basically coming into picture because of this configuration. And then you have another capacitance, you have the substrate, you have the substrate resistance, you have the substrate capacitance, and then you have again the oxide capacitance, you have the substrate resistance, you have the substrate capacitance, so on and so forth. So this is basically how you, this is very weird, but this is how you basically model these inductors in these particular circuits so that you can take into account all of those effects simultaneously. The capacitive coupling, the metallic resistance, which will be always there. So this is just like the equivalent circuit of a inductor. So now I talked about the Q factor, which is basically there might be one question about this Q factor. What I talked about is that this Q factor is simply what you desire, the desired output, and what is undesired. Okay, this is just like a layman definition of this quality factor. Just like I told you in the resonance, you want in the resonance, which is basically the resonance at some particular frequency. When the resonance happens, when the external frequency matches this particular frequency, which is called as resonant frequency, this peak should be as sharp as possible. Okay, so that's why you define there something called as quality factor. You define how sharp is this particular peak. Okay, you define that in terms of what is the bandwidth of this overall and what is the point where this maximum peak is occurring. That you define in terms of that you define as a quality factor. Also, this quality factor has certain more, I should say, definitions in terms of the energy storage, in terms of the energy stored in the inductor and the capacitor, so on and so forth. It depends upon which domain you are talking about. The quality factor's definition slightly changed, but this definition is always kind of a general layman definition that it is something or is the ratio of something which is desired to the something which is undesired. Okay, so when you talk about, let's say, for example, this plot I showed here. Let me just take this plot, duplicate it. I showed you this plot where the quality factor basically becomes zero at self-resonance frequency. Okay, that means you want this quality factor ideally to be huge. That is the fundamental thing because you want this desired component to be large compared to that of the undesired component, which includes certain maybe let's say parasitic effects, other effects, non-ideal effects. You don't want them to be in your system. So you want the quality factor to be huge. That is one thing. But you see that at beyond the self-resonance frequency, the quality factor vanishes. That's why you want to operate your inductor in this particular regime. That is the point I discussed. So when you see the equation for the quality factor in case of these inductors, it depends upon the QLF, KSL into KSR. So what are these factors? This is basically the lossy factor, which is basically the low frequency quality factor. Low frequency, it determines basically the losses because of the resistances and other things. So this is because of substrate loss. This is because of substrate loss factor, and this is because of the loss factor corresponding to the I should say substrate resistance. Okay, so this is because of the substrate resistance again, and this KSR should be ideally equivalent to 1, ideally. Okay, the value of the KSRs and these KSLs is less or equivalent to 1 greater than 0. If it is ideally 1, you want the quality factor to be huge. If KSR reduces, that means more of the loss is towards the substrate resistance loss is huge. Then there will be leakage path of the currents towards the substrate, and that is going to be detrimental. That is going to make KSR, let's say for example 0.2, and that is directly going to affect the Q because Q will be reduced. Okay, so what basically happens now? Let me just take one more page. For example, what happens is that at self-resonance frequency, that means omega greater than omega self-resonance frequency, the L almost behaves like C. It's just like a capacitive coupling, not the exactly it becomes like a capacitor. It just like this capacitance becomes dominant in these particular systems. Okay, now what do we have? We have, for example, I talked about. Let me just see whatever we have covered. And where are we? Okay, we talked about the quality factor. We talked about the capacitances. We talked about electric fields, losses. What else is there? Ground plane. Okay, we talked about it. We also talked about the proximity effect. The proximity effect is basically uh, this proximity effect I talked about. Yeah, I don't think the name matters. The proximity effect is this thing, the currents flowing in the same direction, they are reinforcing each other. So this is advantageous, but then again here the currents are basically flowing in the opposite direction. But that's why these particular dimensions matter. Okay, so these dimensions are going to matter. These distances they are going to matter in terms of the capacitances also, as well as the inductances, as well as yeah, as well as the inductances. Now what else is there? What else has been covered? Let me just see. Introduce TC. Okay, there is electromagnetic wave propagation that is basically covered. Let me just check one more thing. CMOS inductors has not been covered. Yeah, one more thing is transformers, but that's not really covered in depth. That's just like the overview. And you know about transformers, they are basically implemented with these inductors. So you have something called as mutual inductance and the self-inductance. So if you have two inductors lined like these, then you have the current flowing in these based upon the coupling of these magnetic energy from one inductor to the other based on the coefficient of the mutual inductance. So if in on the microwave circuit, what basically it is used. So these are all fabricated at micro fabrication level. Okay, this is not like a huge transformer, just like the one supplying power to us. These are like micro fabricated in the micron dimensions, micrometer dimensions. What are they used? They are basically used for power splitting, maybe power splitting, power combining, and other things. Most of the time, they are used for these particular processes. Let's say you have certain maybe 10-watt power coming, and you want 5 watt to go in this direction and 5 watt to go to the other direction. And in that case, transformers play a great role. Also, it plays a role if you want to combine the powers, if you want to maybe some incoming power and then throw it into some chip where it can process that particular power or microwave power without distorting the signal, then you use these particular transformers. Then you have something called a lateral coupling and the vertical coupling of a transformer. If you fabricate a transformer in this direction in the same plane, then it's basically called as lateral coupling. That if you have a transformer in the vertical plane, which is basically almost like a height, then it's basically something called as vertical coupling. And you know that the voltage of a transformer is L di by dt minus M di2 divided by dt. This is I1, this is I1, This is I2. These are just like simpler current voltage equations that you have talked about. Okay, now the K factor of a transformer basically it depends upon the gap turns, which is basically the if you have a spiral inductor, then it depends upon this particular gap turns. Okay, so that's why these dimensions are important because they are also going to determine the coupling of these in these particular transformers. Okay, now I don't think this has been covered in detail, so there is no need to worry about this particular topic. So what is now there? If we talk about the capacitance is another, I should say, a passive device. So we are talking about the passives here, the inductors, the capacitors, bond wires, the wire bonding, the de-embedding, and other things. Here, if you have the quality factor, I told you the quality factor is desired divided by undesired. Okay, so here you can also define it like if you have some desired energy minus the parasitic let's say parasitic energy or parasitic magnetic energy in case of the capacitor. This is basically the capacitor stores the electric energy in the form of the electric field, but this is the parasitic field divided by 2 pi times the parasitic energy loss per cycle. So this is the just like how you define the quality factor of a capacitor, and you can define it as 1 over omega Rs Cs. And if you check, it should be unitless because Rc has the units of time, omega has the units of 1 over time, so this is unitless quantity. So the quality factor is basically unitless quantity. So if you have, let's say, omega tending to infinity, the quality factor tends to zero. That means at high frequency, the quality factor reduces drastically in in the capacitor systems. Okay, so this quality factor is high for capacitor, so it's usually limited by the inductors. That means if you have, obviously, you are talking about when you are talking about a system, you are talking about both resistors, inductors, and capacitors all together. You never have a separate inductor or you never have a separate capacitor or a separate resistor. All of these occur simultaneously in the system. So that whenever you talk about quality factor, you have to talk about quality factor in terms of all of these components: capacitor, inductor, as well as resistor. Resistor we don't mainly deal about. We're talking about the capacitor and inductor. Okay, so if you see that, for example, this quality factor is high for the capacitor, but it's low for the inductor at certain frequency, then it's going to be limited by the inductor. Okay, because whatever is the lowest one is going to be limited by that. Okay, the slowest one always limits the particular this particular ratio. Okay, now where does this capacitor come from? For example, you have any maybe we're talking about a CMOS. If you have a dielectric, you have a gate, then there is coupling to this substrate. Okay, and these couplings can be sometimes good for RF signals because the RF signal can directly shunt. This is something called as RF shunt. They can directly go to the other end, and but it's not suitable for the DCs. Okay, they can be sometimes suitable, but sometimes they cannot be. But these are, I should say, the capacitive couplings are always going to take place, and they are with respect to the substrate we're talking about. Let's say this is some n plus, this is n plus source, this is drain. Okay. Now we have something called as MIM structure. MIM structure. And what is MIM? It's simple. It's just like a capacitor, just like a fancy name they have given. You have a metal, then you have a substrate, and you have another metal. This is what is called as MIM system. This is, let's say, for example, silicon nitride, can be silicon oxide, or so on and so forth. And in this case, the capacitance is, you know, that it's epsilon s divided by the into area divided by the thickness of this particular dielectric. Okay, and where do you use these MIMs? Mostly they are used in varactors, which have been covered, I guess, in week 5 or week 6. I don't know, but they have been covered in something called as tunable capacitors. Tunable capacitors. Okay, where you can these can be used for the phase changes. These can be used in the voltage controlled oscillators and other things. Okay, so they are able to tune the delays also. Okay, and depending upon the capacitance value, let's say for example, you can tune the capacitance from C max, and you can lower the capacitance to a minimum of C. You can tune the capacitance value from these between the maximum value and the minimum value, some maximum value to some minimum value. Then there is something called as tuning ratio. That basically is the ratio of C max over C min. How good you can tune these capacitors basically to control the delays, time delays and other things. Because you know that time delays is a product of R into C. So if you can control the C, you can control the time delays. And in certain applications, these time delays are really important. Let's say, for example, you might have heard about phased arrays, phased array radars. Phased array radars basically is a concept that this is, for example, a array which is basically throwing a microwave out. This also sends the microwave. This is a microwave sending device. This is a microwave antenna. Also, this is a microwave sending device. So what happens basically, these microwaves are basically combined in an array-like fashion. Okay, and whenever the microwave comes out, it comes out with certain radiation pattern. The radiation pattern is just like a the lobe of the radiation which is coming out of. Let's say, for example, if you have a dipole antenna, then you have, for example, a radiation pattern which looks something like this. There's a minor loop, there's a minor lobe, not loop, there's a major lobe. This is basically showing where the maximum of the electromagnetic energy is going. So this is where the maximum of the electromagnetic energy is going. So this is exactly I should say mathematically, it's basically the ratio of, it's basically the product of electric field and the magnetic field. This is something called as Poynting vector. Maybe you might have heard from the electromagnetic basics. So it's basically showing, the Poynting vector is showing the direction of the maximum energy transfer or the power transfer, in what direction is basically mostly propagating. So this is that particular lobe which shows basically the direction or the radiation pattern of the of this particular simpler system, a dipole antenna, let's say. Similarly, whenever the microwave comes out of an antenna, it comes out in certain pattern. And if you have, let's say, for example, the microwave comes here in this pattern, and microwave comes here in this pattern, in this pattern, in this pattern. Similarly, you have so other patterns coming out from an array. Whenever you have an array of these antennas, what you can basically do is that now you know that if you have all of these microwaves in same phase, they are going to be all in the same direction. Okay, but there is a important thing that if you can change this phase somehow, change the phase somehow. Let's say, for example, you make the phase of this point one, you make a point one times, let's say, point one of phi. For this, you make point five times phi. You make point seven times phi, and for this, you have phi, you have phi. Let's say phi is some phase. What you can basically do brilliantly is that you can steer this. You can steer the direction of the microwaves, just like if you are using a torch. You are using a torch and you are steering it in different directions with the help of your hand. But here you don't have to move your torch. Okay, you have to just give a different phase to the signal, and that phase can be basically changed with the help of these delays. That is very a beautiful concept. That means if you have, for example, if you have a that means if you have this array, and if you have these array of microwave antennas, you can basically make the wave go in the particular direction, in this direction only, in this direction, without basically turning the antenna towards it. So that all of those waves basically go in this direction. And you can also, if you also again tune the phases, you can make all of those waves go in this direction. It's like a beam forming. You can make again tuning the phases, you can make them go in this direction. It's a beautiful concept which is basically used in radar. Military systems use it most often. The drones use it. The jamming antennas use it. All of those systems use it, and you don't have to move this physical system, you just have to change the phases. And how does this happen? This basically happens because if you change the phase of microwaves coming out of it, you're basically destructively and constructively creating interference patterns. Okay, so if you can interfere the waves constructively and destructively, you can create regions of high amplitude and lower amplitude. Okay, just like if you have a wave and if you have another wave out of phase, then these two are going to cancel each other. Similarly, if you have another one wave like this, another wave like this, another wave like this, they are going to constructively interfere and give rise to a huge wave. Similarly, if you just tune the phase slightly, just like if you have another wave like this, and if you have, let's say, for example, another wave maybe like this, then it's going to create interference pattern. Okay, it's going to create interference pattern in such a way that certain regions or certain directions there will be minimum amplitude, certain regions there will be maximum amplitude. And when you tune it in a perfect way, most of the amplitude of the wave goes in this direction, and you can steer the wave now without moving the antenna. Okay, that is how it is done most of the times. This is something called as phased array antennas. Phased array antennas. Okay, and this is a very phenomenal concept, basically, and it's almost used in all of the systems. This is also used in, I should say, mapping. It's used in maybe radars. It's used in lidars. Whenever you have a wave, it's used in acoustic mapping also. You can fire the acoustic waves, and you have the acoustic phased array antennas. You have the microwave phased array antennas. There are a lot of opportunity, I should say, and this is basically I should say most of the time used in these defense and technical applications. So this is just one example that just came to my mind. And now, for example, if we talk about where are we? So we have 1 hour left. Okay, what have we covered? Just went into this. Okay, object bonding. Okay, now if we talk about briefly about something called as off chip bonding or something called as wire bonding. Wire bonding. Now, if you have a, let's say, a certain system, you want to, if you have certain system, you have a certain chip, you want to take out the signal from this particular chip. Let's say this is ground, then you want to, then for example, this is gate, this is drain, this is gate, then you're connecting the probes in this fashion. This is a probe, this is a metal pad, CPW pad, this is another probes, three probes coming, this is a metal pad, and you want to take out these signals, then you can measure the S parameters, then you can measure all of those parameters in order to quantify the signal or quantify the signal or characterize it in simpler aspects. Okay, now these are wire bonds are basically thin metal wires. If you have a chip, these are thin metal wires which are basically bonded to the chip in order to take the output or they characterize it. And they are bonded by, let's say, for example, temperature. There can be pressure applied on it in order to bond it to this. There can be ultrasonic waves used in order to bond it. Okay, but note that these are going to add extra resistance in the system. Okay, as well as there is going to be extra inductance in the system, which is approximately 1 nanohenry per millimeter of this bond wire. This is the approximate value used in the industries as well as commercially. So if you go on increasing the length of this bond wire, you are going to increase the inductance of this particular system. So you have to be very careful in using the bond wire. So what happens most of the time when you have a if you have a system, if you have a die like this, you make a hole in the middle of the die. Exactly, the hole thickness is exactly equal to that of the chip thickness. Then you put the chip inside the hole so that it exactly fits into this hole, and there should be no protruding part out from this chip. It's like a the upper surface should be flat so that when you bring the wire bonding metal wires, they should directly go here instead of going like this. Okay, if there is certain thickness out of the die, then they will make an arc, and if they make arc, the length is going to increase and inductance is going to increase. Okay, then they will be detrimental. So that's why you wanted it to be like these. The wire bonding wire should be exactly in the plane, and there should be no out of plane component of the chip in the when you place it in the die. Okay, so the number of wires also play a key role. How many number of wires you use? How many number of wires you use for the wire bonding? And typically, if you see the inductance, what happens to the inductance with the as you go on increasing the number of wires, the inductance typically drops. Okay, but what happens to the capacitance? The capacitance increases. And why that happens is because the inductance here, whenever you just have many number of wires connected together, you have just like a parallel combination of the inductances. And when you know that effective inductance will be lowered, As you go on increasing, the number of inductors in the parallel, effective inductance reduces. But if in case of the capacitors, you have the parallel combination of those capacitors, that means the effective capacitance is going to increase as you go on increasing the number of wires. So that's why these are going to have effect on the inductances as well as the capacitances of these particular systems. So that you have to take into account all of these effects. You have to compute these effects of wire bonding and other peripheral systems, whatever you connect to the chip, and that is all has to be taken into account. And now what is other thing? Flip chip bonding is not important. On wafer measurements, we have very different. We have talked about a little bit, and what else is there? Yes. Okay, there is something called as de-embedding. De-embedding, just like a fancy name. I don't know why they use these names. It's just like if you have just like I talked about, you have a metallic pad here. You have a metallic pad here, which basically in order to extract the signal. So whatever the parasitic effects, whatever the parasitic resistances, capacitances, and inductances are basically brought by these metallic pads or external peripherals into the system. When you subtract it from the original values of the capacitances, inductances, and resistances, that is something called as de-embedding. Okay, so in the de-embedding, you subtract the pad effect, or I should say parasitic effect, so that you have the effect of original chip only. This is basically only the active device we are talking about. This is the active device. So all other things apart from this system, all other things are peripherals. So when you subtract the parasitic peripheral effects, or let's say the inductance, capacitance, or the resistance from the active area, that is basically called as DM embedding. Okay, and this is done for die, packages, wire bonds, boards. When you include the resistances of all those components, that particular I should say effect, or I don't call it effect. That particular process is called as de-embedding. It's just like you're excluding the effect of those peripherals. Okay, so that you can consider only this particular active area, active chip. Okay, now what else is there? Now we have the something called a small signal model for these particular two-port devices in terms of you can call it Void matrices or admittance matrices. Okay, let's say for example, you have uh, small signal model, just like a basic small signal model. If you have, for example, a voltage, and then you have let's say you have a non-linear device, just like a transistor. Okay, and you have a current flowing, and here the voltage is basically a function of the current flowing. And if you now give a small voltage over this DC voltage, you give a small voltage delta V, that will result in the flow of current delta I. Okay, now you can write V plus delta V is basically F of I plus delta I, just like this. Now you know that if you want to expand it in, you can expand it in terms of the Taylor series expansion around some small value delta I. You can expand this particular term. And you can write, let's say if you have, from the Taylor series, if you can write Taylor series expansion around some x, delta x, you can write it in terms of f of x plus f dash of x delta x plus maybe f double dash of x into delta x squared divided by 2 factorial plus so on and so forth. There's 3 factorial, 4 factorial, so on and so forth. But if you want to include only the linear terms, then you can include only these particular two terms. There's something called as linear approximation. Linear approximation. That means you can write f of x plus delta x in a linear approximation as f of x plus f dash of x into delta x. Okay, but this is only applicable if delta x is small perturbation. This is something called a small perturbation limit. And this is applicable in all of the domains, whether it's quantum mechanics or any other domain. Just don't want to go into it. It's just like simple maths here. Okay. Now, when you linearize it, you can write these in terms of the in terms of the if you want to write these in terms of the voltage and the currents, you can write delta V to be equivalent to F dash of I into delta I. That is as simple as that you can write. Okay. Now, if you have, let's say, for example, a two-port system where you have for example, you have a two-port system, just like how you model these particular devices. You have certain incoming currents I1, you have the voltage V1, and let's say, for example, there is current I2, then there is V2, and if you give certain change again, you have, let's say, V1 plus delta V1, that will result in the flow of I1 plus delta I1, that will result here in I2 plus delta I2, and you will have V2 plus delta V2. You can basically write I1 as a function of V1 comma V2. You can write I2 as a function of it will be another function V1 comma V2. Note that these two are different functions, not the same functions, because they are on the opposite end of this two-port network. And now in terms of if you can write these, you can write these equations in terms of the matrix. How you can write? You can basically write this the perturbation terms. You can denote the perturbation terms, which are basically these particular terms. These are the perturb terms. Perturb terms. Perturb means disturbance, small disturbance you have given. You can write small delta I1, small delta I2, basically given by they are related to small delta V1, small delta V2 by something called as Voy matrix here. So this is something called as admittance matrix. It's just like inverse of the y is the inverse of the impedance. So basically it's like I equals to y times v. This is basically I equals to v over z. This is just like Ohm's law, but in terms of the admittance. Okay. Now what are these basically small values? You can basically think of these small values just like, let's say, for example, this is a gate voltage, this is a drain voltage. Okay, just like here, you can denote these particular voltages in a similar fashion. This is just like how you I should say show a schematic of a field effect transistor or a BJT, okay, or any of the MOSFETs, whatever you show. Okay, and in terms of the, let's say, for example, this Y11, it is basically the change in the function F1 with respect to V1. This Y12 is basically change in the function with respect to V2. This y21 is basically change in the function g with respect to v1, and this y22 is basically change in the function g with respect to v2. These are something called as y parameters. Now, if you inverse them, you get the z parameters or whatever you like to do with this matrix. And you can always convert the y into z. You can convert h into other. You have y parameters, you have z parameters, you have h parameters. You have all of those parameters in terms of the matrix forms, and you can always convert one into another. Okay, they are quite commonly asked questions in, I guess, gate examination as well. So now you can write the equation for the small signals in terms of, let's say, for example, small I1 is equal to y11 v1. This is basically small plus y12 v2. You can write I2 is equivalent to y21 v1 plus y22 v2. Okay, you can write these equations directly, and if you want to convert it into a model, you can model it something like you have a voltage V1, and you have certain maybe admittance here, which is Y11. Then you have current flowing I1, that is going to be this particular thing. Then you have a current source, which is Y12 times V2, which is basically a voltage dependent current source. And then you have, if you talk about now I2, that has to be on the other side. You have I2, basically this is then V2, and you have another source which is Y22, and you should be having another current source which should be Y21 times V1, and then you can connect these two. This is basically the equivalent small signal model of this. And in terms of the, let's say, if you want to relate it with respect to the transistor, FET. This is source, this is drain, this is dielectric, and this is gate. Then basically the electron, let's say if this is grounded, you have applied certain potential here, and you have applied certain voltage, gate voltage here, and if the channel is formed, the electron will go in this direction, the current will flow in the opposite direction. This is drain current ID. Let me show it in terms of ID. Then then this basically, let me write it ID. Then this particular current basically is ID, which is GM times VGS. Okay, and this particular Y22 is basically the output resistance. Okay, it's output resistance, which is basically the ratio of ID with respect to VDS. You know the output resistances. If you have output characteristics of a transistor, it ideally looks like this. But if there is a slope in this, it gives rise to a resistance, which is called as output resistance, and which is detrimental. You don't want this thing to happen, but it's always there, and it's also because of the channel length modulation and other things. That's what you have studied in from the basic physics, basic classes. And this particular admittance is most of the times the gate to source capacitance. So this is basically something called as input capacitance. Okay, and this V1 is VGS, which is the gate to source voltage, which is this voltage. VGS. Oh, not grounded. This is some voltage, and this is, let's say, some plus, some minus. This is VGS voltage. Okay, that's what how you relate these particular models with respect to that of a transistor. And why, let's say Y21 is here, this GM, which is the transconductance parameter. This is just simplest small signal model of a of these particular FETs, how you can convert this particular equation from writing the Taylor series expansion and going into the circuit part of it. But this course was not about the circuit course; it was purely about the devices, particularly the device physics. So that's why most of the time we have tried to explain the device physics and not the circuits, because the circuit is a different level altogether. You have to only deal with the circuits in the circuits course, and that is basically the microwave circuits, where you can basically see how you are going to make these particular circuits, use the different combination of the circuits in order to manipulate the currents, voltage, how you make the power amplifier in a real sense. But here we were talking about most of the time the device physics concept, how the, let's say for example, you have a LGAN, you have GAN, how the 2D layer behaves, what is the maybe a brief about how the energy states are formed in these devices, how the little bit brief about the quantum mechanics. That is what basically this course was all about. Okay, and now if we talk about going into the questions, yes. So if we go into the questions are pretty much now the cakewalk, because not a lot, this should be cakewalk, because these are all theoretical questions, and I hope after checking this session, you'll be able to easily solve them. Just like if you talk about skin depth, which is defined as the skin depth is defined as just I told you what is skin depth. If you have a conductor, then if you give it a microwave frequency or any AC signal, not the microwave, any AC signal which is fluctuating, which is having a positive and negative components. It can be an electromagnetic signal. So it tends to flow near the surface, near the periphery, rather than into the bulk, because of the I should say the back EMF generated. The back EMF basically concentrates it more towards the periphery than into the center, and most of the current flows near the surface or the periphery. It is the similar effect that of the what happens basically at the high frequency in case of the optics. We talked about the absorption coefficient. So I talked about this in the first two slides. So what happens basically if you have, let's say, a metallic bar, and let's say this is thickness Z, and if you draw a graph of, let's say for example, this is, let's say for example, electromagnetic wave amplitude, then it falls off exponentially towards the bulk. Okay, it's just like similar to that of the what happens to the intensity of any of the light wave passing through a medium. Basically, it follows this principle. Dou I rate of change of intensity with respect to this z is proportional to minus I times z. So when you solve this, you get I of z equals to I naught e to the power minus alpha times z, where this alpha is basically something called as absorption coefficient. And you can write alpha equals to 1 over delta. This delta is basically penetration depth, Okay, and it plays a similar role to that of the skin depth. Skin depth here shows the depth up to which the amplitude of the electromagnetic wave falls to 1 by E of its value. Okay, that simply comes because of here. If you have intensity of electromagnetic wave at feeding intensity as Iz, okay, not feeding intensity. If you want to measure the intensity as a function of the depth, okay, and this I naught is the initial intensity, maximum intensity, then you can basically write it in terms of this exponential form, which basically that is what all of the nature follows. It's followed in the radioactivity, it's followed everywhere. So the rate of change of certain quantity is equivalent to the negative of that particular quantity. And if you put, let's say, here alpha equals to I should say 1 over delta, okay, and at z equals to delta, you have I naught e to the power minus 1. So you have I naught divided by e. So that's why you have I z over I naught is equivalent to 1 by e. That means the, or you can in fact write it I naught over e. That means the intensity, this is I naught, let's say. The intensity falls to 1 by e of its initial value, peak intensity, at this particular value, z equals to delta. That means the most of the wave is going to be penetrated up to this layer, and that is the most of the wave is going to travel near the periphery surface. So this region will be unused. This thickness will be unused. It will be redundant. Okay, that is the answer of this question. So the thickness of the conductor of electromagnetic wave attenuates to 37% of its peak intensity. That is what you call as skin depth. Now, the skin depth, what I talked about here, the skin depth is basically a frequency dependent quantity, which is basically defined in terms of the resistivity, the frequency, and the permeability. And it depends upon the material parameters and the frequency what you feed it. So that means if you go on increasing the frequency, you reduce the skin depth. That means more and more wave will be just traveling over the surface. Okay, it is just like absorption coefficient in terms of the light. If you have a metal, if you shine the light to the metal, most of the light reflects. Why? Because the penetration depth of the light into the metal is very small, few nanometers, 10 nanometer. This is the absorption depth of the light. Okay, this is just like a similar concept here. And let's say, for example, if you have UV, UV penetrates very smaller into the metal. If you have, let's say, IR light shined on the metal, IR will penetrate little deeper into the metal. And if you go on increasing the wavelength or reducing the frequency, let's say UV has a frequency of around 100 terahertz, or not 100, I should say 800 terahertz UV. IR has a frequency of around 10 terahertz. You see, if you go on reducing the frequency, you increase the absorption depth. That is the similar thing what happens here. If you go on increasing the frequency, you reduce the penetration depth. Okay, so that is the effect with this particular frequency. But here in this case, it is more because this is an optical domain. Here, this effect is mostly because the effects are similar, the physics is similar, but in these microwave devices, because they are carrying currents, so here it's because of the because of what should I say, the back EMF generated. But in the optical domain, this effect is mostly because of the real part of refractive index plus the imaginary part of the refractive index comes into picture. So this imaginary part of the refractive index creates losses in the medium, and this is what determines the penetration depth of the electromagnetic wave inside the medium. And this imaginary part, I should say, refractive index is related to the permittivity also. So the refractive index you can write as square root of permittivity. In other words, you can write refractive index in terms of epsilon 1 plus iota times epsilon 2. So there is something called as imaginary refractive index also. Let's not go into that detail, but this is just like if you want to study it in more depth. So now you have to use this equation in order to evaluate the skin depth of a rod. When you put everything, you are given everything. It's just like you are given resistivity. You don't have to change the units. It's ohm meter. You're given permeability in Henry per meter. This is permeability. You're given frequency 10 gigahertz. Pi is a constant. You get delta to be around 846 nanometers. This is the value of the skin depth. That means if you have a rod, let's say of maybe 2 micron, which is 2000 nanometer, then if you feed an electromagnetic wave to this, it's going to only travel through the periphery and only go deeper by 846 nanometers. Rest of the approximately 1200 nanometers of this wire is going to be unused. The current is not going to flow in that part, and that will be unused throughout this its entire life. So it's just like it's redundant. That's why most of the time when if you know the skin depth of the wire, then you want to keep the depth, you want to keep the thickness of the wire as small as possible so that you don't waste the wire much. But that there's a problem. If you want both DC as well as AC to flow through the wire, then you have to take care because this effect does not happen at DC. Okay, the DC travels through the bulk entire of the wire instead of just only on the periphery or the surface of the wire. Okay, so that's why whenever the metal lines are deposited onto any of the chips, most of the time this thickness is kept large because these metals not only carry AC but they also carry DC. Okay, just like if you have whenever you give any bias to the system, you give bias plus small signal, which is AC. This bias is basically DC, and you have a small signal which is fluctuating. So you have constant DC, over it you have small signal which is fluctuating. That's why these metallic wires carry both AC and DC. That's why they are not kept thin. If they had to only carry AC, then they would have been kept thin, but they have to carry both AC as well as DC, so they are kept thicker than the expected value computed from the skin depth. Just a little bit about it. Another one is for a microstrip line, if the thickness of the dielectric is H and the width of the conductor is W, then increasing the W by H ratio. That's what we talked about here, I guess. Where did we talk about it? Yes, yes. So if we increase the W by H ratio, the effective dielectric permittivity is going to get increased, and what is going to happen? The characteristic impedance is going to reduce. That is the effect of increasing the W by H. And that's what I have discussed. So if you have W by H goes on increasing, the effective permittivity goes on increasing, increasing the effective dielectric constant, and decreasing the characteristic impedance of the line. So that is what is basically shown by those plots. So this is epsilon effective, this is Z naught. So epsilon effective increases. Let me show it for only one epsilon. Epsilon effective increases and Z naught reduces. That is basically the effect of changing the ratio of this W in a microstrip line by H. So that most of the time you want the electric field to be penetrated in the substrate rather than it should not leak towards the air. This is not desired. Okay. Now again at self-resonance frequency, the quality factor of integrated inductor goes to 0. Why? I talked about that at omega equals to omega self-resonance frequency, the quality factor becomes 0. So inductor no longer behaves like an inductor. It changes the sign. Just like if you have a quality factor, if you have a frequency X is this, let's say this is self-resonance frequency, the quality factor goes on maximum and then it dips. And this is the point of this is 0 basically. So the quality factor becomes 0 at self-resonance frequency. And there is a huge capacitive coupling that comes into picture at very high frequency beyond omega greater than omega self-resonance frequency. Okay, so beyond this, it almost behaves like a capacitive, and in this region it is inductive. It's inductor. Okay, that's what also we discussed. Now to minimize the electric coupling of an inductor to the substrate, yeah, this electrical coupling we also discussed. How can you how can you minimize the electric coupling of an inductor to the substrate? You can increase the dielectric thickness, or you can choose a smaller area inductor. We're talking about this thing again. That's what I have talked about. So you can go on increasing the dielectric thickness, which is this H, or you can choose a smaller inductor area. If you go on, but there's a catch. If you go on reducing the area, the inductance is also going to come down. So there's a trade-off in choosing this particular area. So you cannot tune the basically if you want to tune the area, then you are going to play with the inductance also. But that's what basically is the question. If you want to minimize the electric coupling of an inductor to the substrate, so that there is less coupling with the substrate. Coupling of what? Coupling of inductor, because there is a shunt path of the inductor. If you have an inductor, just like I showed you the equivalent circuit of an inductor, there is this path also, which is towards the substrate. So if you want to negate this path, you can basically make the H larger. Okay, so that most of the this part of the equivalent circuit is neglected. Most of the currents should flow through this inductor, and there will be no coupling of this. Okay, that's what is basically something called as electric coupling. Electric coupling. The Q factor of a capacitor dash with the increase in frequency. What happens to the Q factor of a capacitor? If the frequency increases, the Q factor reduces. That is what we talked about. The Q factor of a capacitor is omega R C Rs times Cs. That's what is basically going to happen. No, rather it reduces parabolically. What is given? Did we discuss it? Okay, it reduces parabolically. Okay, we discussed about it. Q factor of a cap. I think we discussed it. Where did we do? Hmm. Yes. Okay, so it reduces with respect to the change in the frequency based on this particular relation. Now here note that this RS does not change with frequency, at least up to certain values. You have a constant resistance. It does not change, but this capacitance is going to change with the change in the frequency. And as a result, because the I should say the capacitive reactance is omega times C. So if you go on increasing the frequency, the XC reduces. That means it becomes almost like a short. Yeah. So if you go on increasing the this, it's going to impact. Yeah, it's fine. It's going to increase the Q factor of the capacitor. So now the regarding the bond wires or whatever you call it, wire bonding or whatever you may like to call it. So you have an active device and you connect it with certain peripheral wires so that you can characterize it and you can take the current voltage values and you can compute the S parameters. The bond wires as compared to integrated inductors have a higher Q value. That is absolutely correct. They have the higher Q quality factor Q values. Okay, but overall inductance increases as the number of bond wires increase. No, we have seen that if you have an inductor and if you have the number of wires, bond wires, then the inductance goes on reducing because it's just like you have a parallel inductors, and you know the L effective reduces as the number of if this is L1, this is L2, this is L3, so the effective inductance comes down. So the statement one is correct, but the statement two is incorrect. That is the answer of this question. So moving on to in the given matrix, the empty matrix this is quite simple. The empty matrix should be uh, is it like V equals to yes, this should be like impedance matrix, the inverse of it. I showed you the I matrix to be equivalent to something like this. This is admittance here, but this is V equals to some matrix times the I. So here it's impedance, okay, and this is Z equals to 1 over Y. This is Y. This is Z, just like Ohm's law. And just like here, you have a impedance matrix Z11, Z12, Z21, Z22. Similarly, similar to what I showed you in the Y matrix case of the in the small signal case, small signal model. Okay. The process of removing the effect of peripheral measuring elements to obtain the pure device parameters is known as, yes, that is known as wire de-embedding. That's what I told you. If you have an active device and if you have side peripherals, let's say this is ground, and then you have, let's say this is drain, this is gate. What am I showing? This is ground, then you connect the uh, pads, the metallic pads. You connect the pads like this in order to extract the characterize this device. Then this particular thing is the active area here, where you have the actual device, this thing. The other things, this, as well as this, they are something called as peripherals. Okay, and whenever you subtract the effect of the peripherals from the active device, that is basically called as de-embedding. That's what I have showed. So you need to subtract the capacitances, voltage, capacitances, resistances, and inductances, which occur because of all of these peripherals from the active device. You have to subtract all of those in order to compute the actual values. There are also wire bondings. Okay, so all of those effects which have to be subtracted and in the effect called as de-embedding. Okay, so that's it in this session. And I guess this was the final session as of final week 12. This was the final session, and I hope you guys like this particular course. It was quite a heavy course for someone who is not having a good knowledge of the device physics, because that was prerequisite in it. It was impossible to cover everything from the basics, because it's not a purely basic level course, because the prerequisites were device physics as well as some part of the electrostatics. These were the prerequisites. You should be knowing those things. But I tried to cover some of those things in my lectures. If you have watched those lectures carefully, I tried to cover all of those things which were discussed in the prior week. I tried to discuss those in the weekends. So that's it from my side. I'll be taking off. But before that, we have one more session where we are going to recap. We're going to have certain doubts. If you have, we are going to discuss a little bit about current research problems and what is the future outline. And this particular session will be on Wednesday from 11 a.m. to 1 p.m. Okay, on the in the same link, and that will also be uploaded on the YouTube channel, as well as the same procedure will be followed, except it's on Wednesday. So that will be the final sum up of the course. That is, we are not going to solve any questions in that. Just I'll try to recapitulate what are the important things in this course, what are the current research problems which you can focus, what are some of the tools you can use in order to simulate it. Fabrication obviously I cannot show, but I can show you certain things which are done in the research. What are the trending topics, so hot topics? What are the topics used in the industrial sectors, commercially, academically? What are the important topics? So that's what we are going to deal in this extra session. We are done for today. I hope you like this particular session. So if you have no more questions, then you can leave. Otherwise, you can stay. Thank you.